In this video, I'm going to show you some examples of finding partial derivatives. F of x and y is tangent inverse of y over x. And for this function, we want to find the 4 second partial derivatives. So we want to find f sub xx, f sub xy, f sub yx, and finally we want to find f sub yy. These are the 4 partial derivatives, the 4 second partial derivatives of this function. For finding second partial derivatives, first we have to find the first partial derivatives. So we have to start with f sub x and f sub y. Before we start, let me remind you the formula of derivative of tangent inverse. Derivative of tangent inverse of an expression, say u, is 1 over 1 plus u squared. So derivative of tangent inverse of y over x based on this formula is 1 over 1 plus u. Here u is y over x. So y over x squared. But don't forget, based on chain rule, we have to multiply this by derivative of the inside function. So here also we have u prime. If u is a function, we have to multiply this by u prime. So now we have to multiply this by derivative of y over x. But note that when we want to find derivative of y over x, y is a constant and x is the variable, because here we are finding the partial derivative with respect to x. If we use quotient rule for finding derivative of y over x, derivative of the top is 0 times bottom is 0 minus derivative of the bottom function, which is 1 times by the top function y over the denominator squared. So derivative of y over x is negative y over x 2. So multiply this by negative y over x squared. Now let's simplify f sub x, because it's better to simplify this and then it helps us to find these second partial derivatives easier. Note that y over x here squared is actually y squared over x squared. So here we have 1 over 1 plus y squared over x squared times by negative y over x 2. If here we do a common denominator between y over 2 over x2 and 1, we have 1 over x squared is here, x squared plus y squared times by negative y over x squared. Now here in this fraction we have 1 over this fraction, which means reciprocal of this fraction. So this equals to x squared over x squared plus y squared times by this. Now if you look at the numerator here and this denominator, we can cancel x2 with x2, and so finally we have negative y in numerator and x2 plus y2 in denominator. So finally we can say the partial derivative with respect to x is negative y over x squared plus y squared. Now let's find the partial derivative with respect to y. Again, based on the formula of derivative of tangent inverse, we have 1 over 1 plus y over x all squared. Don't forget to multiply this by derivative of the inside, which is y over x. Derivative of y over x with respect to y is 1 over x. Here, for finding derivative of y over x with respect to y, we don't need to use quotient rule. Note that the variable y is only in numerator, and in denominator we don't have any y. So this expression is something like y over 3, y over a constant, y over 10. What is the derivative of y over 10? 1 over 10. What is the derivative of y over 3? 1 over 3. So what is the derivative of y over x? 1 over x. But if you use quotient rule, you can get the same answer. But it's not necessary to use quotient rule for finding the derivative of y over x. Without quotient rule, it is obvious that the derivative of y over x with respect to y is 1 over x. So multiply this by 1 over x. If we simplify this, similar as we did here, easily you can check that this equals x over x squared plus y squared. Let me show you how you can simplify this. Again, if we do a common denominator here, we can write it as x squared plus y squared over x squared times by 1 over x. This x squared goes to the top, so we have x squared over x squared plus y squared times 1 over x. If we cancel 1x from the top with 1x from bottom, x remains in top, and so this is x over x2 plus y2. This is how you can simplify the expression. Now we are ready to find the 4 second partial derivatives. Let us start with f sub xx. For finding f sub xx, we have to take the derivative of f sub x with respect to x again. So f sub xx is the derivative of this fraction with respect to x. If we use quotient rule, derivative of the top function is 0 times bottom is 0 minus derivative of the bottom function times by the top function, or top function times by derivative of the bottom function. The top function is negative y, but don't forget we have a negative in the formula of quotient rule. So we have y times by derivative of the bottom, which is 2x, all over x squared plus y squared squared. And you can write this as 2xy over x squared plus y squared all squared. Now let's find f sub xy. For finding f sub xy, we have to take the derivative of f sub x, which is this expression, with respect to y. Again, if we use quotient rule, the derivative of the top function with respect to y is -1 times by the bottom function minus the top function, which is -y. So again, we have plus y times by the derivative of the bottom function with respect to y, which is 2y. So y times 2y all over the bottom function squared. If we simplify this expression, we have -x2 minus y2 plus 2y squared. -y squared plus 2y squared is y squared, and we have a -x2 here, so this expression is -x2 plus y2. So numerator is -x squared plus y squared, and x2 plus y2 squared is denominator. Now let's find f sub yx. We know that it should be equal to this expression, but here we want to evaluate this and to check to see if it is really equal to this or not, which based on the Clairaut's theorem, it should be equal to this expression, because we know that f sub xy and f sub yx are almost always the same for most of the functions. For finding f sub yx, we have to take the derivative of f sub y, which is this expression, with respect to x. The derivative of the top with respect to x is 1 times by denominator minus, write the top function, which is x, times by derivative of the bottom function with respect to x, which is 2x, because the derivative of x2 is 2x and the derivative of y squared with respect to x is 0. So the derivative of the bottom function is 2x all over denominator squared. If you simplify the numerator, you can see that it equals y2 minus x2, and this is the denominator. And as you can see here, this expression is the same as this expression. So f sub xy and f sub yx are the same. Now let's find f sub yy. We have to take the derivative of this expression we have with respect to y. Derivative of x over x squared plus y squared with respect to y is derivative of the top with respect to y is 0. We don't have any y here, and the derivative of x with respect to y is 0 minus, write the top function, which is x, times by derivative of the bottom function with respect to y again. The derivative of this is 0 and the derivative of y squared is 2y all over denominator squared. Numerator is negative 2xy and denominator is x2 plus y2 squared. These expressions are the 4 second partial derivative of this function. Let's do another example. In this question, we want to show that the function u equals sine of kx times by sine of akt is a solution of this equation. U sub t equals a squared u sub xx. So we want to prove that this function is one of the solutions of this equation. This equation here is one of the famous equations in physics, and it is actually the wave equation. So we want to prove that this function is a solution for the wave equation. Note that in this function, k and a are constants, and only x and t are the variables of this function. So u is a 2-variable function. First, we have to find the first derivative of this function, u sub t and u sub x. The partial derivative of this function with respect to t is sine of kx. Note that in this part of the function u, we don't have any t. So this part of this function is just a coefficient for this term. So when we take derivative with respect to t, every variable other than t is a constant. So everything here is a constant, is coefficient for this part. So we write sine of kx, and now we have to take derivative of sine of akt. Derivative of sine is cosine, so cosine of akt. But don't forget, you have to multiply this by derivative of the inside. derivative of sine is cosine, but based on chain rule, we have to always multiply by derivative of inside. What is derivative of AKT with respect to t? A and k are constants, and so derivative of AKT with respect to t is AK. So the partial derivative of u with respect to t is AK sine of kx cosine of AKT. If you want, you can write this as AK, because this is a constant. It's better to put the constant first and then sine of kx cosine of AKT. Now for finding the second partial derivative with respect to t, we have to take the derivative of this expression again with respect to t. So u sub t is everything here is without t, so it is a constant, so we have to write that ak sine of kx. Multiply this by derivative of this part. Here we have variable t. Derivative of cosine is negative sine. So negative sine of AKT. But again, don't forget to multiply by derivative of inside. Derivative of AKT with respect to t is AK. AK times AK is a squared k squared, and don't forget we have a negative here, so u sub t equals negative a squared k squared sine of kx sine of AKT. Now let's see what is u sub xx, the second partial derivative of u with respect to x. Again, first we have to find u sub x. For finding the derivative of u with respect to x, everything here is without x, so it is a constant, it's coefficient for this part. So only we have to take the derivative of this part and multiply by this constant. You don't need to use any product rule for finding the derivative of u with respect to x, because only x is here and this is a constant. The derivative of sine is cosine kx. Don't forget to multiply by derivative of inside. Derivative of kx with respect to x is k, and I prefer to put k here. And of course we have to multiply this by sine of AKT. So u sub x is this expression. Now for finding u sub xx, we have to take the derivative of this with respect to x again. K and this expression are constant when we take derivative with respect to x, and only we have to take derivative of this part. So let's write the constants first. K is a constant, sine of AKT is constant. Only take derivative of the variable part, which is cosine of kx. Derivative of cosine is negative sine of kx multiplied by derivative of inside of cosine, which is k. If you multiply this k by this k, and don't forget we have a negative here, so this equals negative k squared sine of AKT sine of kx. And this expression is u sub xx. Now we have to check to see is u sub tt equal to a squared times u sub xx. Note that u sub tt as we evaluated here, is negative a squared k squared sine of kx sine of akt. It should be equal to a squared times u sub xx. U sub xx is this expression. If we multiply this expression by a squared, which we have here, a squared times u sub xx is, if we multiply this by a squared, we get negative a squared k squared sine of akt sine of kx. Note that here you can write sine of kx first and sine of akt after that. Now if you compare this expression with this expression here, you can see that they are equal to each other. So it shows that this function is a solution for the wave equation. Let's do another example. In this question, we want to prove that this function u is f of x plus 80 plus g of x minus 80 is a solution for the wave equation. Let me remind you the wave equation. U sub tt, the second partial derivative of u with respect to t, equals a squared u sub xx. So we want to prove that this function is a solution for the wave equation. Note that here we suppose f and g to be two differentiable functions of any order. Actually, twice differentiability of these two functions is enough, but we can suppose they are differentiable of any order. So we want to prove that this is a solution for the wave equation, which means that if we take the derivative of this function twice with respect to t, it should be equal to the derivative of this function twice with respect to x times by a squared. First, we find u sub x, the derivative of u with respect to x. Derivative of f, which is an unknown function, is f prime. So derivative of f of x plus 80 is f prime of x plus 80. But don't forget, when we find derivative of any function, we have to multiply it by derivative of the inside because of chain. Derivative of the inside, derivative of x plus 80 with respect to x is 1, because derivative of x is 1 and derivative of 80 is 0. In 80 we don't have any x, and derivative of 80, because it's constant with respect to x, is 0. So derivative of f of x plus 80 with respect to x is f prime of x plus 80. Plus, now we have to find derivative of g of x minus 80. Derivative of g, which is an unknown function, is g prime. And again, we have to multiply it by derivative of the inside. Derivative of the inside with respect to x is again 1. And we don't need to write 1 here. Derivative of x is 1, derivative of 80 is 0, and so derivative of the inside is 1. So this is u sub x, the derivative of u with respect to x. Now let's find u sub xx. Now we have to take derivative of this expression again with respect to x. Derivative of f prime is f double prime. Write the inside of that, and don't forget to multiply by derivative of inside, but derivative of inside is again 1. Plus derivative of g prime is g double prime. Multiply by derivative of inside again is 1. And so u sub xx is this expression. Now let's see what is u sub t actually. U sub t is derivative of this function with respect to t, derivative of each term with respect to t. Again, derivative of the function f is f prime. Leave the inside, but don't forget to multiply by derivative of inside with respect to t. Derivative of x is 0 because we take derivative with respect to t, and derivative of any term without t is 0. So derivative of x is 0. But derivative of at with respect to t is a. So don't forget to multiply this by a plus. Now take derivative of this part with respect to t. Derivative of g is g prime, and multiply by derivative of inside with respect to the t. Derivative of inside is negative a because derivative of negative at is negative a, and derivative of x is 0. So u sub t, the partial derivative of u with respect to t, is a. Because a is constant, it's better to put constant a first and then multiply by f prime of x plus at minus a g prime of x minus at. Now we have to take derivative of this with respect to t again. For finding the derivative of this term with respect to t, a is a constant, so we write it a, and then we have to take derivative of f prime. Derivative of f prime is f double prime. Write the inside. Don't forget to multiply by derivative of the inside. Derivative of at again. Derivative of x is 0. Derivative of at is again a, and if we multiply a by this a, we have a squared here. Minus a, derivative of g prime is g double prime, x minus at. If we multiply this by derivative of the inside with respect to t is negative a. So we have to multiply this by a negative a. But this negative a times by this negative a is plus a squared. So we can write plus a squared here. So the second partial derivative with respect to t is this. So u sub t is this expression. And we want to prove that this expression equals a squared times yu sub xx. If we multiply a squared in this expression, a squared times u sub xx, if we multiply a squared in this term and in this term, we have a squared f double prime x plus at plus a squared g double prime x minus 80. And as you can see, this expression and this expression here are the same. So this shows that this function here is a solution for the wave equation. And this completes this question. The next question, if u is a function in the form of e to the power of b1 x1 plus b2 x2 plus bn xn, and if b1 squared plus b2 squared bn squared equals 1, so if this sum equals 1, then based on these conditions, we want to prove that the second partial derivative of u with respect to x1, the second partial derivative of u with respect to x2, and the second partial derivative of u with respect to xn, this sum equals u. For finding the second partial derivative of u with respect to x1, first we have to find the first partial derivative, the derivative of u with respect to x1. Note that here u is a function with n variable. x1 is one of the variables, x2, x3, so on till xn. So this function u has n variable, and here we want to find the derivative of u with respect to the first variable x1. Let me remind you the derivative of e to some expression. The derivative of e to any expression is the same function. Don't forget to multiply by the derivative of the exponent. So if we use this formula for finding the derivative of e to this expression, the derivative of e with respect to x1 is first write the same function and multiply this by derivative of the exponent with respect to x sub 1. None of these terms have x sub 1, so the derivative of all of them with respect to x1 is 0, and the derivative of b1 x1 with respect to x sub 1 is just b1. Note that here b1, b2 and so on to bn are constants, and so the derivative of b sub 1 x1 is just b1. Now if we take the derivative of this expression again with respect to x1, we can find this. So for finding this, we have to take the derivative of this expression with respect to x1. b1 is a constant, so let's first write b1, and again we have to take the derivative of this expression. The derivative of e to the b1 x1 plus b2 x2 up to bn x sub n is again the same function. Don't forget to multiply it by the derivative of the exponent, which is only b1 again. And if we multiply this b1 with this b1, so we can write this as b1 squared. So the second derivative is b1 squared times e to the b1 x1 plus b2 x2 and so on up to bn xn. Because of the symmetry in this function between variables, if we do the same calculation for x2, we can get the same expression, but the difference is that instead of b1 squared we have b2 squared. For the next variable we have b3 squared, and finally for xn we have bn squared. So if we continue doing this, we can say that the partial derivative of u, the second partial derivative of u with respect to x1 squared plus the second partial with respect to x2 squared and so on up to the partial derivative with xn squared is equal to b1 squared times e to the b1 x1 plus b2 x2 bn xn. The second partial derivative is exactly the same, but instead of b1 squared we have b2 squared, so we have b2 squared times by exactly the same thing, so e to the b1 x1 plus b2 x2 and so on up to bn xn. And if we continue this, we have bn squared e to the b1 x1 plus b2 x2 bn xn. Between all of these terms, e to b1 x1 plus b2 x2 plus bn xn is common. So if we factor that, we have e to the b1 x1 plus b2 x2 plus bn xn times b1 squared, b2 squared, bn squared. But from this, we know that the sum is 1. So we know that the sum of these numbers, these constants, is 1. So this equals 1. And if this equals 1, what remains is this expression. And this, if we look at the question again, is u. So this shows that the sum of these derivatives equals these, and this is actually the original function that we had here. So this equals u, and this completes this equation. I hope you enjoyed this video, and see you in the next videos.